Natalie, and I'll be doing problem 73.
I'm Jackie, and I'll be doing problem number 65.
Hi, my name is Natalie, and I'm going to be presenting number 73 of limiting reagents today. The problem begins with, if you have 50 liters of hydrogen chloride gas and it reacts with 10 liters of oxygen gas, what is the volume of chlorine gas produced? So I have my chemical equation up here, and before you can do anything, you have to balance your equation so that you have the same of each product on both sides. So in order to do that, you need to have a total of 4 of each of the CLs and 4 of the H's and 4 of the O's. So in order to do that, you're going to put 4 in front of the HCl. You're going to put a 2 in front of this Cl, because this times this is going to give you your 4 Cls. Then you're going to do a 2 in front of the H2O. That's going to give you your 4 H's and your 2 O's. Okay? So now that we have the equation balanced, we can move on from there. Okay, and because this is a volume equation, that means that I don't have to do any of the converting to moles or anything. I can go right into my equation, which I'm going to do because it's asking for the liters of the chloride gas. So I'm going to start out with my given, which is my 50.0 liters of hydrogen chloride. So I'm going to go 50 LHCl, and it's a gas, and I'm going to do my dimensional analysis. Dimensional analysis, you really can't go wrong with it. You're going to always end up with a good product at the end. Okay, so I like to do my bracket. So what I'm going to do is I'm going to use my 2 Cl2 up here, and my bottom number is going to be my 4 HCl. And as you can see from this, you can cross out the HCl's on the top and the bottom. And what you're going to do is you're going to multiply straight across. You're going to go your 50 times your 2, which is going to give you 100. Your 100 is then going to be divided by your 4. So in the end, you're going to end up with 25.0 Cl2. That's the product that you're trying to yield. So your volume of chlorine gas. So this is the first product. So now I need to go, there's another given up here, 10 L of oxygen gas, okay? What I'm trying to get to is the chlorine gas at the end, okay? So my next given is 10 liters of O2 gas, all right? My dimensional analysis again, can't go wrong with that. Then I'm going to take my 2 liters of Cl2, which is right here. That's going to go on top. Okay, and it's going to be go on top of 1 liter of O2, which is where this comes in. So my 1 liter of O2. Remember, they're all gases. Okay, so now I can do this problem. What I do is I do the same thing. I'm going to multiply this times this divided by 1. And that's going to give me 20.0 Cl2. And as you can see, this is going to be my limiting reagent because it's the smaller of the 2 products.
Number 65, and it states if 1 gram of aluminum hydroxide reacts with 3 grams of sulfuric acid, what is the mass of the water that's produced? The formula that you start with is the aluminum hydroxide plus sulfuric acid yields aluminum sulfate plus water. First, what you have to start with is you have to first balance your equation. And to balance it, you're going to need to put the coefficients 2, 3, and 6. Why we're doing this is because you need to make sure that you have an equal number of all of the elements involved on each side of the equation. So for example, we start off with 6 hydrogens here, plus another 6 hydrogens here, is going to equal our 12 hydrogens that we get on this right side. And if you go through the equation, you're going to make sure that everything's balanced. If it is, you can proceed to your dimensional analysis step, which starts out with, you're either going to pick your 1 gram of aluminum hydroxide to start with, or your 3 grams of sulfuric acid. I'm going to start with the 1 gram of aluminum hydroxide. So we have 1 gram of the AlOH3. Start with that. And you're going to think about what you need to convert it to your next step, which you're going to need the molar mass for, of your aluminum hydroxide. To get your molar mass, you have to look at the periodic table and kind of break down the different elements that are in it. So to start with, we're going to see that we have an aluminum, an oxygen, and hydrogen are base elements in aluminum hydroxide. Aluminum, oxygen, and hydroxide. By looking at their mass number on the periodic table, it helps you to further get what its mass as a whole is. So for aluminum, we're going to start with 26.98 grams. For the oxygen, it's 16 grams. However, we have a 3 on the outside of the parentheses, which means there's 3 oxygens in your equation. So we're going to multiply that by 3. We're going to do the same thing with your hydrogen, which is 1.008 times 3. Can we cut real quick? Okay, so for the oxygen, when you multiply it by 3, you're going to get 48 grams. You're going to get 3.024. What you do from there is you add your 26.98 grams with your 48 grams and your 3.024 grams, which is going to give you a grand total of 78.004 grams of aluminum hydroxide. You then plug this number back in this original dimensional analysis. So you're going to take 78.004 grams of aluminum hydroxide. The thing about this conversion here is that you know once you get your grams of aluminum hydroxide, once you get the whole thing, you know that that is equal to 1 mole of the aluminum hydroxide. From there, you do your mole-mole conversion. And to do this, you look at your ratio from your beginning coefficients. So we know that we want to get to water as our end result, and we're starting with aluminum hydroxide. So we have 2 moles of aluminum hydroxide down here, and we go look at our water, we have 6 moles of water. But we're not done yet because we want to get water back into grams. So we come over here and do 1 mole of H2O water. But we have to do the molar mass for water now, which we're going to use in both parts of our equation anyway. So if we come back over here, we know that there is hydrogen and oxygen in water. The mass of oxygen, once again, 16 grams, and the hydrogen being 1.008. But we're going to multiply it by 2 because there's 2 in there. So multiply that by 2. It's going to give us the 2.016, altogether 18.016 grams of H2O. We're going to bring that back down here, put it in our equation. I know it's a lot of back and forth, but how to do it.
Why do you have to do it?
Why do you have to do it back and forth? It's because if you don't get this mass to begin with, you can't convert back into grams. So you need the molar mass to continue. All right. So then we just treat the top like a multiplication equation. And you are going to get this nice, awesome number of 108.096. Do the same thing to the bottom. Once you multiply that out, you get 156.008. Divide it. Get this lovely decimal. What I do is I take the number straight from the calculator and just kind of write it out for reference later in case you mess up in some way you can see what your original was. But you have to take into account the significant digits of your beginning numbers and translate that to your end of your equation. So we're going to have to round to right there. So in the end you get 0.693 grams of H2O. And how we ended up in grams is you go through your equation, you have to make sure everything cancels out. Grams, grams, moles, 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 and moles, which leaves you in grams over here, which means you have grams of H2O. Second part of the problem. You come back, we're going to start again, but this time we're going to be using the sulfuric acid as the first part of our equation. So 3 grams of, sulfuric acid, H2SO4. So we're going to try to start out the same way that we did before. But just like in the beginning of our problem, we're going to need to come back over here and find yet again another molar mass, but this time both for sulfuric acid. So we have, I wish I was taller, so we're going to get a chair. Okay. So we have a hydrogen, we have a sulfur, we have our oxygen. So we have, let me see, we have 2 hydrogens, so hydrogen, and its mass number of 1.008 times 2. Our sulfur is 32.07 grams, and then our oxygen is 16, but like we did before, because it's 4, we're going to be multiplying that by 4 as well. Well, we don't need that there, because 32 times nothing is 32. There we go. So our oxygen is going to be 64. Our hydrogen is 2.008 0.016. And these are all grams. When you add all of those up, you're going to get 98.086 grams. Yay. No more chair. We're going to come back, put this in our nice dimensional analysis equation that we have going. 98.086 grams of 2x4. All right. And then we're going to go back, just like we did the first time. We're going to look for the sulfuric acid. So we have the 1 mole of sulfuric acid is equal to this. So we might as well write that right now. So 3 moles of the 3 moles that you get from here. We're going to use the same 6 moles of water that we used in this first equation. So 6 moles. We have to once again convert moles of water back into grams of water. So 1 mole of water. And then we can just steal the 18.016 grams that we got from before and put that right in here because it's going to be exactly the same. Saves you a little time. When we do the lovely multiplication on the top, we are going to be left with, oh, that was on my lovely other sheet. Almost. So we're going to be left with 324.288 divided by 196.172. Just like I said before, you don't have to do this. I just like writing out the long number just in case I mess up somewhere. And we are left with 1.65 grams of water. Because the decimal 0.693 is significantly less than 1.65, this is going to be all the water you're going to get out of it, and aluminum hydroxide is your limiting reactant.
Hi, my name is Minwen. I'm going to do problem number 69, and the problem states that 70 milliliters of nitrogen gas reacts to 45 milliliters of oxygen gas. What is the volume of the dinitrogen trioxide that's going to be produced? So, how I arrived to this is this is our original equation. And from this, the equation is not balanced because from here we could see that there's 3 oxygen while there's only 2 oxygen over here. And in order for us to balance it, we had to actually use these two. The numbers are different, so we're going to use the lowest common denominator to try to balance it. So from here, we're going to use 6 as a total. So in order to get 6, we're going to have 2 more, 2 in front as a coefficient. So we'll get 6 oxygens. Here we'll use 3 as a coefficient to get 6 oxygens. So from here we can see that there's actually 2 times of the dinitrogen, so that's going to be 4 nitrogens. In order to get 4 nitrogen, we just need to add 2 more on here. Okay, from this, we're going to have 2 parts to the problem. What we're trying to go to is the limiting reactant to dinitrogen trioxide. So first part is 70 milliliters of nitrogen, and the second part is 45 milliliters of oxygen. And our goal is to get to how much is it gonna react to the nitrogen trioxide. Okay, so for here we need to figure out the unit factors that's gonna eliminate these two and just arrive at dinitrogen trioxide. So from here, the first part is, okay, we're gonna use these coefficients in our unit factors. So the first one for nitrogen is
And what are those that you're doing right now, Min?
I'm just writing out the unit factors from, okay, so how I got to this, why it's 2 ml is because we're using the coefficients for the nitrogens here.
Mm-hmm.
So, okay, the neat thing about the volume conversion problems is that when the metrics, which is 70 and 45 are the same the same metrics, then we could just use that and go straight from moles, which is usually it's supposed to be 2 moles of nitrogen over 2 moles of dinitrogen trioxide because of our coefficients, where that's how we got to here. But because it's the same, we can actually just replace the moles and use it the metrics of 2 milliliters in each. And from here, we notice that we need to eliminate the N2, and so we figure out that in order to eliminate, the bottom coefficient has to have N2. So we're going to use this one for our nitrogen. And we're going to do the same thing for our oxygen, which is same thing. We have these as the coefficients from the oxygen, which is 3 ml, which we just pretty much from as stated earlier that we're gonna replace the moles and just use milliliters. And the 2 milliliters came out the same as the coefficient from here, and we just bring it down. Okay, so from this, I'm also gonna use, since I'm trying to eliminate the oxygen, and this one contains the oxygen as my denominator, I'm gonna use this as well. Okay, so from here, my thing is times this by 2 ml of N2O3 over 2 ml N2. So my milliliters of nitrogen is crossed out. And from here, I can actually just eliminate, it's 1-to-1 because it's 2 over 2 is just 1. So I could just eliminate that. And from that, I have, so I just times across because it's just So right now it's just 1:1. So this whole the bottom denominator is gone. So I have what is remaining is 70 milliliters, 70 ml of ml of NO2. And my bottom one is gonna be the same. I'm gonna use this. So it's 2 ml N2O3 over 3 ml O2. So I'm able to eliminate the ml part here, and what is left is 45 times 2 ml of dinitrogen trioxide over 3. So the easiest way for me to do this is just actually 45 over 3 is actually 15. And 15 times it by 2, I will arrive at 30 ml of dinitrogen trioxide. And from here we can see that 30 ml is much less than 70 ml of dinitrogen trioxide. So 30 is my limited reactant.
Hi, I'm Terry. I'm going to be doing problem number 59, which is asking to find the mass of iron produced in 40 grams of iron as it reacts with 10 grams of magnesium. So the first thing that I'm going to do is make sure that the initial equation is balanced. So taking the first element, which is iron, we're going to look at the left side of the equation. There's one iron over here and one iron over here. Next is to look at the oxygen, which there's one oxygen here and one oxygen over here. And last is the magnesium, and there's one magnesium on the left and one magnesium on the right. Now I know everything is 1 to 1, and so the equation is balanced. So the second thing I'm going to do is I like to establish my reference points from the beginning, which is to determine what the mass is going to be of each element that we're working with so that we can convert that to moles. So the first element we're going to look at from the periodic table is iron, and we're going to find that iron is equivalent to 55.85 grams. Next, we're going to find the mass, or the grams, of oxygen, which is equivalent to 16 grams. And next, we're going to determine the grams of magnesium. And the magnesium is equivalent to 24.36 grams. So now that we've looked at the mass of each element individually, we're going to go ahead and do one more thing, which is to determine what the mass is of our iron oxide. So to do that, we're going to go ahead and add the iron and the oxygen. And that adds up to 71.85 grams. Okay? Now that we have our mass converted to moles to start with, and we have a balanced equation, we're going to go ahead and determine the mass of iron produced in both iron and the magnesium. So first, let's start with the iron oxide, and this is going to be part A of our problem. So we're starting with 40 grams of iron oxide. And we're going to utilize our numbers that we came up with to start, which is our iron oxide that we calculated over here to convert it to moles. So 1 mole of iron oxide is equivalent to 71.85 grams of iron oxide. Next, we're going to standardize our moles of iron oxide to our moles of iron. So we're going to say 1 mole of iron over 1 mole of iron oxide. And our iron, which we initially got from the periodic table, is 55.85 grams of iron. And that was equivalent to 1 mole of iron. Okay, now it's just a matter of canceling everything out. So our iron oxide is canceling out here, and our moles of iron oxide is canceling out, our mole of iron and our mole of iron. And next you simply multiply the top numbers, divide them by the bottom, which should give a total of 31.09 grams, or 31.1 grams of iron. So next we're going to determine the iron produced from the magnesium. And we're going to start with our given, which is 10 grams of magnesium is equivalent to 1 mole of magnesium. And we're going to check over here, which is going to be 24.36 grams of magnesium. And next we're going to bring in our iron. And our magnesium. And our iron, which we have from up here, which again we found in the beginning, 55.85 grams of iron, all over 1 mole of iron. So our 10 grams of magnesium, or no, our magnesium, our grams of magnesium cancel, our moles of magnesium cancel, our moles of iron cancel. And again, if you multiply the top, divide it by the bottom, you come up with 22.97 grams of iron, or 23 grams of iron. So now we simply need to compare the result of our iron produced from our 10 grams of magnesium, which came out to be 23 grams, compared to our iron oxide, our iron produced from iron oxide, which is 31.1 grams. And since 23 grams of iron produced from the magnesium is the least amount, this has been determined as our limiting reagent. Thank you.